Welcome to this coding walkthrough. In this session, we'll tackle problem number 1323, titled Maximum 69 Number. This problem is a fun and approachable exercise that challenges us to apply efficient thinking to maximize a number by making a single-digit change. Let's dive right in and explore the solution together. In this problem, we are given a positive integer called number that consists only of the digits 6 and 9. Our goal is to determine the maximum number we can obtain by changing at most one digit. Specifically, we can either change a 6 to a 9 or a 9 to a 6, but we're limited to making just one such change. The input to this problem is a single integer, number, and the output is also a single integer, which represents the largest number we can achieve after making the optimal change. For example, if the input is number equals 9669, the output should be 9969, because by changing the first 6 to a 9, we achieve the maximum possible value. Let's look at more examples to understand this better. For the input number equals 9669, we can change the first digit, which is a 6, to a 9, resulting in 9969. This gives us the largest possible number by modifying just one digit. In another example, if the input is number equals 9996, we can change the last digit, which is a 6, to a 9, resulting in 9999. This is the maximum number we can achieve here as well. However, if number equals 9999, the number already consists of all 9s, so no changes are needed. The output in this case would remain 9999. Let's now look at some additional details and constraints for this problem. When the input is number equals 9999, the output is 9999 because the number is already maximized with all 9s, so no changes are required. Looking at the constraints, the value of number will always be between 1 and 10,000, and it will only contain the digits 6 and 9. This means we don't have to worry about other digits appearing in the number. Some edge cases to consider include when number is made up of all 9s, where the output will simply be the input, as no change is needed. Another edge case is when number consists of all SAXS, such as 6666. Here, the optimal solution is to change the first 6 to a 9, resulting in 9666. Lastly, if number is a single-digit number like 6 or 9, the result will depend on the value of that single digit. Change it to 9 if it's 6, and leave it as is if it's already 9. To start, let's consider the brute force approach. The idea here is to generate all possible numbers by flipping each digit of the input number, from 6 to 9 and then determining the maximum result. Since the problem guarantees that the number only contains the digits 6 and 9, the number of possible variants is limited to flipping each occurrence of 6 one at a time. The process involves converting the number into a string or list of characters to make it easier to manipulate individual digits. Then, for each digit, if it's a 6, we temporarily flip it to a 9, calculate the resulting number, and keep track of the maximum value encountered. Finally, we return the largest modified number. While this method works, it is computationally inefficient because it evaluates every possible variant, even though the optimal solution only requires one targeted change. The time complexity is O, D, where D is the number of digits in the number, and the space complexity is also O, D, because we store modified versions of the number. This inefficiency makes the brute force approach less desirable compared to others. Now, let's move to a more efficient solution, the optimized approach based on replacing the first instance of the digit 6. The key insight here is that to maximize the number, we only need to change the first occurrence of 6 to 9. This is because digits in higher positions have a greater impact on the overall value of the number. The process involves converting the number into a string or list of characters, which allows for easy traversal and manipulation. Then, we search for the first digit that is 6, change it to 9, and reconstruct the number. This approach is much more efficient than brute force because it targets the change that has the most significant impact on the result. The time complexity remains O, D, as we still traverse the digits, but we avoid unnecessary computations. The space complexity is also O, D, due to the string representation of the number. This method is not only faster but also simpler to implement, making it a clear improvement over the brute force approach. Additionally, there's an alternative mathematical approach that avoids converting the number into a string. Instead, it directly manipulates the digits of the number using arithmetic. The idea is to extract each digit of the number using division and modulus operators, starting from the least significant digit. By tracking the position of the first 6 encountered, we can mathematically replace it with 9 and reconstruct the number. While this approach is space efficient, with a space complexity of 1, it's less intuitive and more prone to implementation errors compared to the string-based method. The time complexity remains OD, as we still need to process each digit. However, the added complexity in handling digits mathematically makes this approach harder to implement and debug, which can be a drawback in practice. Given these options, the chosen strategy is the string-based optimized approach. This method strikes the perfect balance between efficiency and simplicity. While the mathematical approach is slightly more space efficient, the string-based approach is much easier to implement and debug, making it the preferred choice in most cases. On the other hand, the brute force approach was ruled out due to its inefficiency and unnecessary complexity. The core insight that makes the optimized approach so effective is realizing that we only need to change the first occurrence of the digit 6 to maximize the number. This targeted operation eliminates exhaustive computations and simplifies the solution to a single traversal and replacement. When comparing approaches, the brute force method is conceptually straightforward but computationally wasteful, while the mathematical method, though efficient, is harder to implement correctly. The string-based approach, however, achieves a strong balance, making it the ideal choice for this problem. Finally, the implementation uses the string-based optimized approach to ensure clarity, simplicity, and efficiency. By focusing on a single traversal to locate and replace the first occurrence of 6, this solution avoids unnecessary complexity while achieving the desired result. This method provides a clean and straightforward solution to the problem, making it both practical and effective for solving the maximum 69 number challenge. The problem we're tackling here is to maximize a given number that consists only of the digits 6 and 9. You are allowed to change at most one digit in the number to achieve the highest possible value. For example, if the input is 9669, changing the first 6 to a 9 gives us 9969, which is the maximum value we can get. The output in this case would be 9969. To solve this, we first need to understand the key observation: since 9 is greater than 6, changing as 6 to 9 always increases the number's value. The greedy insight here is that we should prioritize changing the leftmost 6 to 9, as digits on the left contribute more to the overall value of the number. If the number contains no 6s, it is already maximized, and we can simply return it as is. To design the algorithm, we start by converting the input number from a string into a mutable data structure, such as a list of characters. This makes it easier to modify individual digits. Next, we traverse the list of digits from left to right. During traversal, if we encounter a 6, we change it to 9 and immediately stop the loop, as only one change is allowed. Once the modification is complete, we reconstruct the number by converting the list of characters back into a string and return the result. It's important to handle edge cases, such as when there are no 6s in the number. In that scenario, no changes are needed, and we can simply return the input as is. This approach also handles single-digit numbers seamlessly, as the loop will process the single character just like any other input. The algorithm is both efficient and straightforward. It operates in O(n) time complexity, where n is the number of digits in the number, because we only traverse the digits once. The space complexity is O(1) in terms of auxiliary space, as no additional data structures beyond the input list are required. Converting the string to a list allows us to easily manipulate individual digits, and converting it back to a string ensures the output matches the expected format. Here's the Python implementation. We first convert the input string into a list of characters. Then, we iterate through the list and replace the first 6 we encounter with 9. Once the change is made, we exit the loop and return the modified list as a string. This simple yet effective approach ensures correctness and efficiency, even in edge cases like already maximized numbers or single-digit inputs. To analyze the algorithm, the time complexity is O(n), where n is the number of digits in the input, as we traverse the list of digits at most once. The space complexity is O(n) for the input list, but beyond that, no additional space is required. Let's walk through an example with the input 9669. First, we convert the string into a list of characters 9, 6, 6, 9. As we traverse the list, we skip the first digit, 9, but at index 1, we find a 6. We change this 6 to 9 and immediately break the loop. The modified list now looks like 9, 9, 6, 9. Converting this back to a string gives us the result 9969. For an edge case like 9999, we convert the input to 9999, but since no 6 is found during traversal, no modifications are made. The output remains 9999. In the example of 9999, the lack of any 6 means no changes are needed, so the algorithm simply converts the list back to a string and returns 9999 as the output. This demonstrates the natural handling of edge cases by the algorithm. The key takeaways here are that the greedy approach of prioritizing the leftmost 6 ensures the largest possible number with minimal computation. The algorithm is efficient, operating in linear time, and handles all edge cases, including already maximized numbers and single-digit inputs, without requiring additional checks. Converting the string to a list simplifies the process of modifying digits, making the implementation both clean and effective. This makes the solution robust and well-suited for this problem. This solution begins by converting the input number into a string, as strings are easier to manipulate when replacing specific digits. The algorithm identifies the first occurrence of the digit 6 using the in operator and replaces it with 9 using the replace method, ensuring that only one occurrence is replaced by setting the count parameter of replace to 1. If the digit 6 does not exist in the number, the original number remains unchanged. Finally, the modified string is converted back to an integer and returned as the result. This approach ensures that the maximum number is achieved by making at most one digit change. The solution is both time-efficient and simple, with a time complexity of O(n), where n is the number of digits in the input number, since the replace operation scans the string once. This is the Java implementation for LeetCode problem number 1323, maximum 69 number. The solution mirrors the Python logic by converting the integer to a string, using a character array in Java, replacing the first 6 with 9, and converting it back to an integer. Key differences include the use of Java's char for string manipulation and integer.parsint for conversion. The logic ensures only the first occurrence of 6 is replaced, maximizing the number. To solve the problem, we start with the input number 9669. The first step is to convert this number into a string. This conversion allows us to easily manipulate individual digits, which would be more challenging if we kept the number as an integer. After converting, the state of our string becomes 9669. Next, we need to replace the first occurrence of the digit 6 with 9. Since 6 is present in the string, we use the replace method, specifying that only the first instance of 6 should be replaced. This changes our string from 9669 to 9969. Finally, we convert the modified string back into an integer. This gives us the final output, which is 9969. Now let's look at the input 9999. As before, the first step is to convert the number into a string, which results in 9999. This step prepares us for digit manipulation. Next, we check if the string contains the digit 6. In this case, it does not, so no replacement occurs. The string remains unchanged as 9999. Finally, we convert the string back into an integer. Since no changes were made, the final output remains 9999. In the example where the input is 696, the process begins by converting the number into a string. This gives us 696. With the string representation, we then check for the presence of the digit 6. Since 6 exists in the string, we replace only the first occurrence of it with 9. This changes the string from 696 to 996. Lastly, we convert the modified string back into an integer. The final output for this input is 996. The time complexity of the solution is determined by 3 main steps, each of which processes the digits of the input integer. First, converting the integer number to a string takes O(d) time because we need to process each of the d digits in the number. Next, the replace 6, 9, 1 operation scans through the string to find the first occurrence of 6 and replaces it with 9. In the worst case, this operation also takes O(d) time since it may need to scan the entire string. Finally, converting the modified string back into an integer requires processing each digit, which again takes O(d) time. Since these operations are executed sequentially, their time complexities add up to O(d) plus O(d) plus O(d), which simplifies to O(d). This means the runtime of our solution scales linearly with the number of digits in the input number. The space complexity of the solution is primarily determined by the memory used to store the string representations of the number. When we convert the integer number to a string, the new string representation requires memory proportional to the number of digits, which is O(d). Similarly, when we create the modified string after replacing 6 with 9, this also consumes O(d) space since it is another string of the same length. The conversion of the modified string back into an integer does not require additional memory beyond the input size, as Python dynamically allocates memory for integers. Other variables used in the function, such as temporary variables, occupy constant memory, O(1). Since the dominant factor is the storage of the strings, the overall space complexity of the solution is O(d). When comparing this optimized solution to a brute force approach, the efficiency becomes even more apparent. A naive method might involve generating all possible combinations of numbers by replacing each occurrence of 6 with 9, then finding the maximum value among them. If there are k occurrences of 6 in the number, this approach would require generating and comparing 2 to the power of k combinations, leading to an exponential time complexity in the worst case. Additionally, storing these combinations would also consume exponential space. On the other hand, the current optimized solution avoids generating multiple combinations by directly replacing just the first 6 with 9. This results in a much more efficient approach with a linear time complexity of O(d) and linear space complexity of O(d), making it significantly more practical for large input sizes. Analyzing the best, average, and worst-case scenarios further solidifies the efficiency of the solution. In the best case, if the input number contains no 6, the replace operation is skipped entirely, and the time complexity remains O(d) due to the string and integer conversions. On average, the algorithm scans a portion of the string to locate and replace the first 6, which still results in O(d) time. In the worst case, where the first 6 is located at the very end of the number, the entire string is scanned, leading to O(d) time as well. Each step, string conversion, string replacement, and integer conversion, individually takes O(d) time. Since these steps execute sequentially, the overall time complexity is O(d). Similarly, the space complexity, dominated by the storage of string representations, is also O(d), reinforcing the linear scalability of the solution. One common mistake when tackling this problem is focusing only on changing the first occurrence of the digits 6 to 9 and stopping there. While this works well for maximizing the number, it might not be sufficient for variations-based problems where exploring all possible replacements is necessary. Another frequent pitfall is overcomplicating the logic by using nested loops or recursion to generate all combinations of replacements. This approach often leads to unnecessary complexity, especially since a single traversal or selective replacement is usually enough. Lastly, it's important to consider the constraints of the problem. For example, failing to verify the input size or assuming that the number will always include the digits 6 or 9 can lead to missed edge cases, like scenarios where the input contains none of these digits. Being mindful of these common errors helps ensure a robust solution that accounts for all possibilities. Another mistake to watch out for is treating the number as an integer and relying on arithmetic operations to modify its digits. This can introduce unnecessary complexity, whereas handling the number as a string allows for much simpler manipulation of individual digits. Additionally, it's crucial to prepare for cases where the number remains unchanged. If a number doesn't contain any 6 or 9, the logic should gracefully return the original number without error. From an interview perspective, it's important to clarify the scope of the problem early on. For instance, determine whether you're maximizing the number, generating all variations, or addressing another goal entirely, as this will shape your approach. Strive for simplicity. If the goal is to maximize the number, identifying and replacing the first occurrence of 6 with 9 is typically the most efficient method. Be prepared to discuss edge cases, such as inputs made entirely of 9s or SAXS, numbers without any 6 or 9, and even single-digit inputs. Finally, take the time to explain the trade-offs between brute force methods like generating all variations and more optimized approaches, ensuring your interviewer understands your decision-making process. In terms of related problems, the maximum 69 number problem connects conceptually to challenges like reverse integer, palindrome number, and encode and decode tiny URL, as these also involve digit manipulation or transformations. When considering alternative approaches, one optimized method is to replace the first occurrence of 6 with 9 and stop there. This approach is ideal when maximizing the number is the goal, as it minimizes both time and space complexity. The time complexity for this solution is O(n), and the space complexity is O(1). Another approach involves generating all possible variants by replacing every occurrence of 6 with 9, then storing the resulting numbers. This method allows for more flexibility, such as processing multiple replacements or exploring all variations of the number. However, the trade-off here is higher complexity, making it suitable only for problems where such exhaustive exploration is explicitly required. An alternative strategy involves using arithmetic transformations. This approach converts the number into an array of digits, applies arithmetic operations to modify the necessary digits, and then reconstructs the number. While this method can be useful in scenarios where string manipulation isn't allowed, it tends to be more cumbersome to implement and prone to errors. The additional complexity makes it less desirable for a problem like maximum 69 number, where simpler string-based methods provide a more streamlined solution. That said, understanding this approach can be helpful for problems where arithmetic manipulation is a better fit, so it's worth keeping in mind as part of your problem-solving toolkit. Great work! We've successfully solved problem number 1323, maximum 69 number. By exploring efficient strategies and understanding the nuances of the problem, you've added another tool to your problem-solving toolkit. Thanks for watching, and we'll see you next time for more coding fun. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!